So I'm Ziming Liu. I'm a PhD student at MIT studying physics and AI. So today I'm going to talk about, from neural networks to Newton, learning symbolic formulas and conservation laws. So current AI models lack a physical understanding. So if you take video generative models like Sora, when you prompt it to generate a gymnastics, it will generate a gymnast performing a really challenging routine, which is like growing arms out of their legs and growing legs out of their arms. And if you have a robot dog wandering around in your house, and it didn't notice the banana peel on the ground, it will just fall to the ground and kiss the ground. Many AI scientists, AI scientists also suffer from the generalization problem. It can only work well on in-distribution data set, but cannot generalize out of distribution. So why is physics hard for AI? So imagine you observe, this is like an old story. You observe an apple falling to the ground. An AI model may say that everything's related to this phenomenon, like the redness of the apple, the angle of the sunlight, the bird in the tree. So this is a bad representation. But we humans can realize that only the position and the velocities of the apple, or at most some air resistance, is relevant to this phenomenon. So this is a good representation and leading to good generalization. So tracing back to the fundamental incompatibility between AI and physics, I would want to argue that physics is mostly based on symbolism, so here the Maxwell's equations are written down as symbolic equations. So the representation is so nice that you can print the equations on a T-shirt, but you cannot do the same thing for a neural network unless you cheat. Okay, so what makes a good physical representation? So the representation is to first be compact, meaning that they're essential, they cannot be further compressed down, and also because the universe we live in has one-dimensional temporal axis, so we want some temporal regularity. That is, the evolution equation should be somewhat well-behaved. So first I'll talk about how we can discover some static relations just given the state vector, something like symbolic regression, using the Kolmogorov unknown networks. And then I will talk about how we can discover conservation laws from temporal data. So first, if you open a physics textbook, like the Feynman lectures on physics, you see a lot of equations written in different variables, have different structures. But really, they share one common feature, which is compositionality of univariate or one-dimensional functions. So what do I mean by composition of one-dimensional functions? So think of you want to compute the distance between two points in a two-dimensional plane. And the way you do the computation, you can parse it down into this computational tree graph. So besides the addition and the subtraction, everything else are the squared function, the square root function. They're one-dimensional functions. Now the question is, because these physics equations have this structure, which is composition of univariate functions, do today's neural networks capture such nice structure? Before I say the answer no, I want to review a little bit, what's today's theoretical foundation for neural networks. So today's AI is built upon this universal approximation theorem, which states that a function, a high-dimensional function, is approximately a linear combination of some random features. So here sigma is some nonlinear function, for example, ReLU, SciLU, whatever. So this representation is equivalent to this two-layer network. But of course, we can build the network deeper. So this model is known as the multi-layer perceptron, or MLP. So first, MLPs cannot handle 1D functions elegantly. So suppose you are doing an experiment and you see a signal on your oscilloscope like this, and human experimentalists may say, oh, it looks like a wave. It's probably a sine function or cosine function. But the way a neural network, an MLP, sees the function is in a wildly different way. Like it encodes the information into the weights and biases. So if you try to plot the training evolution of the weights and biases of these neurons, you see that it starts from being a rectangle into something that looks like a butterfly. Well, this is just a coincidence. But the question is, how can we tell from this distribution that it is actually a sign function? So moreover, MLPs cannot handle compositionality, at least not explicitly. So although both the parse tree and MLP are kind of deep and have hierarchical structure, they do not have one-to-one correspondence. So it's not easy for you to try to extract out the compositional structure out of MLPs. So now the call to action is we need a new neural architecture to capture such nice structure, which inspires our Kolmogorov-Arnold networks. Down to the very fundamental representation perspective, we need a new representation that is both structured and expressive. We already know how to build a structured representation based on parse tree. So now the only problem is how we can generalize or kind of relax the parse tree into a neural network that is potentially more expressive. So this is the parse tree we begin with. Step 0 is we're trying to unify plus and minus. So it's kind of trivial because x plus y equals x plus minus y. So all the binary operators in this graph now are addition symbols. Step number 1 is making these 1D functions learnable. So previously, these functions are like square root and squared. But now we really want them to be as expressive as possible. So like you can randomly draw a line or draw a curve on a piece of paper. The way we do that is that we want to parameterize these 1D functions with, as well I will talk later, with B-splines. So they are very flexible. And step number 2 is that the sparse tree is still very shallow and not specific to this formula. So suppose if we don't know the structure of the formula, we want to kind of generalize the network. So step 2 is to expanding the network to be wider and deeper. So now, is the expressive power theoretically guaranteed? This is why I love math, because back in 1957, there's already the Kolmogorov-Arnold representation theorem that telling us by constructing a neural network, as I just described, leads to something that's really expressive. So to be specific, the theorem states if f, again, is a high-dimensional or multivariate continuous function, then it can be broken down into a composition of one-dimensional functions. So to be more specific, the representation looks like this. There are double summation symbol. There are also this, outer functions, inner functions, but they are all just, one-dimensional functions taking in one number and outputting one number. So the graphical representation, so this representation is equivalent to this graphics looking like this. So you place this 1D functions on edges, and you place the addition symbol on the nodes. So you notice that this is different from MLPs, where there are 1D functions on the nodes, but like linear weights on the edges. But they kind of, like they're both like densely connected, but simply they place different things at different places. Right. So how do we make these 1D functions expressive? So we use the B-spline parameterization. So a B-spline is a linear combination of some B-spline bases at different locations. So basically, these are like this locally activating piecewise polynomial functions looking like an inverted ball or something, but they're also shifted to different places. So to make sure that you can cover the range, to make sure the function is flexible within that range. What's nice about this representation is that you can switch between fine grids and the coarse grids depending on your, where you want to lie on the Pareto frontier of efficiency versus accuracy. All right, so far the network is a densely connected network, but I motivate this whole thing with the parse tree. So how can we get it back from a dense network? So the answer is actually quite simple, similar to we add, like in MLP, we add L1 regularization to weights, we get a sparse network. So here we also add L1 regularization to edges, which basically encourage this function to be 0 functions. So after training, you can see that most of the edges, they go away, but there's a subgraph that survives. So then we can prune the network to distill it into a smaller network, and then you observe some interesting patterns like this wave thing. Perhaps it's a sine function. This parabola thing is perhaps a squared function. And in the end, you are able to simplify it all the way down to this symbolic form. All right, so just a quick sanity check. We just said that any multivariate function is a composition of 1D functions and addition. What about multiplication and division, which are like the most basic binary operations? So it turned out Ken discovered a really interesting formula which leverages the second-order polynomials for the multiplication, and can also use the logarithm and exponentiation trick for the division, which is kind of expected, but still nice to as a sanity check. So everything so far, the story I told so far, sounds really nice. It is usually the time when something starts to go wrong. So actually, in 1989. Jarosik and Poggiol, they already wrote a paper arguing that the Kolmogorov theorem is irrelevant for machine learning. So do we need to just stop and give up? So let's take a look at why they argued that the theorem is irrelevant. So the smoothness is a central problem. Their argument is that their takeaway is that in the worst case, there's no smooth, exact two-layer representation. So that's a bit mouthful. So let's just break it down. So in the end, we want smooth representations because with smooth representations, we can then take derivatives and do gradient descent. But there are actually three conditions in here, which makes things that look worse. But it doesn't have to be seemingly worse. So let's tackle the three conditions one by one. So actually, we can just tackle the first two problems via the method of spiritual victory. We just say that, well, maybe in the worst, the theorem says in the worst case, maybe we don't care about worst case. We care about typical cases. Like many things we have in physics are actually well-behaved and smoothly varying. So that's fine. And also, maybe we don't care about exact representations. Again, maybe we can win some smoothness back by allowing some approximation errors. And the last thing is a technical problem that we can address, which is we can extend the two-layer representation to deeper representations. And taking the wisdom from modern deep learning, which is just going deeper, because people have shown that there are exponential separation between shallow versus deep neural networks. So we can we can win some smoothness back by stacking more layers. So so now we have deep Kolmogorov networks. The way it is constructed is quite straightforward. So the original representation is two-layer, but we can stack more layers. We can get 3 layers, 4 layers, 5 layers, as deep as we want. So after we have the deep network, the first point I want to argue is that the deep is indeed different. So if you take this 4-variable function, you can pause and imagine a little bit like how many layers you need. So you actually need 3 layers because you need exponential, you need sine, you need the squared function. So if you train a 3-layer CAN network, you end up learning this nice activation functions corresponding, like have one-to-one correspondence to this symbolic formula. However, if you stick to this 2-layer network, you end up having a network which is wider, but also if you take a look at into these activation functions, they're very oscillatory, very not well behaved. So this is exactly what Jarosik and Poggiol argued about. And if you look at the loss function, the 3-layer can achieve much lower loss than 2-layer cans. And for 2-layer cans, there's a huge test train gap, meaning that the 2-layer can is just trying to fit some fake representation by overfitting to the training data instead of trying to finding the true symbolic structure. Well, but every coin has 2 sides. And in the next example, I want to argue that sometimes being shallow is good, or even more insightful. So for example, if you take this equation, which is x plus y divided by 1 plus xy, you do the same exercise to construct a Ka network, I would first imagine that we would at least 5 layers. Because you need 2 layers for the multiplication, you need 2 layers for the division, and you did another layer for the addition or something. But it turned out you can approximate the formula with just a 2-layer Ka network. And by some symbolic fitting, you can realize that this equation is tanh of arctanh x plus arctanh y. So this sounds like a really weird formula. So did we find something that is only approximately true in this region? The answer is no. These 2 formulas are actually equivalent. So if you're familiar with special relativity, you will realize that this is formula for velocity addition in special relativity. And in relativity, we have this rapidity trick, which is exactly turning velocity into something called so-called rapidity using the arctanh function. So in special relativity, rapidity is a better representation than velocity because it naturally accommodates the fact that velocity is limited by speed of light because you have a tanh here. So it lies in -1 to 1. And when you have multiple velocities to be composed together, the operation also becomes easier because you only need to arctanh everything to this arctanh space, add up everything else, add up all the things as if you are adding velocities classically, and then tanh thing back. So everything so far, like known things. So what about things that are unknown? Like, can we discover anything we don't know yet? So well, still it's known, but less known. So in DeepMind's Nature paper published like 3 years ago, they trained an MLP to learn a not invariant data set. So I won't get into this, but basically it's a supervised learning problem, taking in some variables and trying to do some classification in the end. So they used a 4-layer with 300 MLP network. Totally, that's like 300,000 parameters. But our CAN network, you only need 1 hidden layer and 1 hidden neuron. So that's 200 parameters, and achieving similar accuracy. And because the CAN representation is so compact, you can just literally plot it out, and you can understand which variables are important by staring at the Ka graphic representation. But with the MLP, because it's so huge, you need some extra like interpretability method, like attribution method, to figure out which variables are important. Our CAN network also has an unsupervised learning mode, which can discover some more relations, which I'm not getting into here. So the community also used CAN network to do some cool things. So one user on GitHub told me that they are studying ocean science, and they were able to simplify a 75-term expression using CANs into a 2-term expression, and without losing too much accuracy. So again, there's still this accuracy versus simplicity trade-off. So next, not only we want to discover relations between variables, the state vectors is also involved in time. So we want to find temporal regularity. And arguably, conservation laws is one of the most important concepts in physics. So what is conservation law? It's basically you mapping a state vector into a number. And conservation law is saying that that number is not changing over time. So here, you have a harmonic oscillator with position and velocity. And we know that the energy is some squared function of the velocity and position, which is conserved over time. So if you plot the trajectory in the phase diagram, they would form a perfect circle. So one thing to notice is that the orbit is not all over the place, simply because there is energy conservation. It cannot jump off the energy isosurface. So the intuition here is that a conservation law is equivalent to a geometric constraint, saying that this is the no, you cannot go to that zone, because if you do that, you will violate your conservation law. So finding conservation law is a historically challenging problem in physics. For example, Henry Poincaré is famous for, among many other things, first discovering the full complete set of conservation laws for the three-body problem, thus proving that three-body problem is chaotic. And here we're asking, can we take AI models we named AI Poincaré and trying to figure out the conservation laws. First, the number of conservation laws, and then the numerical or symbolic form of the conservation laws. So I won't get into the math here, but I just want to mention the intuition again, that the number of conservation laws is related to the trajectory manifold, because conservation laws are some kind of geometric constraints. So now the problem boils down to estimating the manifold of your trajectories. So you think of your trajectories as some scattered points. Like there's an underlying manifold, and the goal here is to estimate the dimensionality of the underlying manifold. So the technique, I probably don't want to get into this, because it's actually very similar to denoising score matching, like as in diffusion models. But our work was done in 2020, which is roughly the time when diffusion models were out. So at that time, we were not aware that this is actually our diffusion models. But it's very interesting that we start from different motivation, but we end up having something similar, which is a manifestation that diffusion models is indeed a powerful tool, that you can use it to count the dimensionality of a manifold. We tested it on some standard physics problems, and it outperformed other baseline methods like autoencoders, PCA, and fractal method, etc. But counting is not enough. So this is a funny story when I play with my model. So this is a 4-variable system. At first, I thought there are only 2 conserved quantities, but my model told me that there's 3. So I spent like a whole week trying to debugging the model and trying to coaxing the model to say that the answer is 2. Okay, but in the end, I realized that there is indeed a third conservation law, which is just that is just so rare that even textbooks won't include it, but there's actually there. So the problem here is that counting is not enough. We actually want the symbolic formula, or at least some numerical values, to the conservation laws. So in AI Poincaré 1.0, we finished the counting problem, and in 2.0, we're able to find the numerical values of the conservation law by parameterizing the conservation laws as neural networks. And in 3.0, we're adding some symbolic inductive biases so that we're able to find some symbolic form of conservation laws. So now applications. So turbulence is an intriguing but also concerning phenomenon in fluid mechanics in everywhere. And the reason why turbulence happens is arguably due to the lack of conservation laws. So understanding conservation laws provides a complementary perspective to understanding turbulence. So here we studied a simplified fluid mechanics system. It's very simplified. We only have like 4 point particles, but have some weird interactions. Okay, so the dynamics governing these 4-particle system is this, ordinary differential equations, like really long and with some weird constraints. So now the question is how many conservation laws we can discover. So like my human collaborator came to me telling me that they spent the 2 whole months and finding 12 conservation laws, which is already very, very impressive to me. But with AI Poincaré 3.0, it's able to figure out 14 conservation laws less than in 1 minute, and providing the symbolic formulas. And my human collaborator is not convinced that the result is correct. So he actually did the paper and pencil strategy, trying to verify that the 2 actual conservation laws are correct. And that's when he got convinced that that's not a fluke. We also discovered a new conservation law in atmospheric chemistry, whose importance, so it's related to climate change, air pollution. But really underlying it is this differential equations. And Poincaré 3.0 is able to find the 3rd conservation law beyond oxygen conservation and nitrogen conservation, which is quite interesting, but also puzzling. And only a year later, a group of human scientists that wrote a paper saying that they proposed co-production law, which resolves a recent conundrum posed by a machine-discovered candidate for a non-integer conservation law, which was referring to the conservation law we discovered with our AI model. So combining this together with what the human domain experts discovered, this altogether deepens our understanding of chemical reaction networks. So conservation laws not only, we can not only deal with conservation laws on the physical variables we already extracted out, which are like the correct abstract level variables. We can also learn conservation laws from videos, and also potentially building conservation laws into video generative models to make sure that these models are physical. So overall, I think what's interesting is to develop AI models that can efficiently learn from the physical world by building in symbolic structures, conservation laws, and also what Elias talked about, causality, into these models to make them better understand the physical world. So besides this, I'm also generally interested in like science-inspired algorithms, science of deep learning, and AI for science. So I'm happy to chat about this offline. And with that, I think that's everything I would like to share, and I'm happy to take questions. Yeah, please.
Thank you for the excellent talk. I have a question about conservation laws and group symmetries. So there's a relationship between those, and can you get them with your software? And yeah, any comment about that?
Yeah. So like as you said, like the Noether's theorem states that there's a correspondence between conservation laws and symmetries. I think one can also formulate it as discovering symmetries. Actually, there's one work I didn't talk about. We try to discover hidden symmetries like inside some physical data. So maybe someday we can unify their methodologies, but so far it seems like people, there are like two directions, the conservation laws and symmetries. But I indeed, can see that there might be something unified that's lying ahead. But I don't know what's that yet.
Thanks.
Yeah.
Thank you for the very interesting talk. I've not quite understood how these conservation law network work. Like, can you re-explain? And
Sure.
You mentioned connection with diffusion models too.
Yes, sure. So, so as I said, the counting conservation law problem. So that's the first paper I'm talking about. We're actually not learning all the symbolic form of the conservation laws, but we're only able to counting the number of conservation laws. So like here, the task is like you have a bunch of points in 2D. And the goal is to figure out that these 2D points, they actually lie on a circle, like which is one-dimensional. So the way we do that is that we want to obtain a local tangent space by random walking on the manifold. So how do we random walk on the manifold? So we just first add a random noise to the clean data, and then train a neural network to pull it back to the manifold. And this is similar to how the scores are doing in diffusion models. Like the diffusion models are pulling you towards a cleaner distribution. So here it's corresponding to like the clean manifold. That is like the trajectory manifold.
So so you have a trajectory. You add some noise to it.
Yeah.
And you do a PCA.
We add noise to it. We add a Gaussian noise to it, but followed by a network that pulling the noisy point back to the manifold. So showing this plot. So for example, it's a like three-dimensional space, but your trajectory manifold say is a sphere. Then if you just add random Gaussian noise and do PCA, you would get three principal components. But if you pull it back onto the manifold, you would end up having two principal components, which is like a sub-manifold structure we can detect, indicating that there's a conservation law. Because like you cannot go off the third dimension because of conservation laws.
How do you pull it back to the manifold? Like
Yeah. So So this is similar to the denoising score matching objective. You basically force the network to pull it back to the original clean data point. But because you can imagine there's a symmetric point here, which has equal probability to be perturbed to the same noisy point. So the network has to average between pulling it to A and pulling it to B. So end up pulling it to the middle points of X, which is what we actually want. So yeah, this is a bit cumbersome, but the idea is similar to diffusion models, particularly denoising score matching. Yeah. Yeah, great question. So, like we have a predefined library of symbolic functions. We have sine, square. Like here, the training is not depending on the symbolic library. They are like B-splines, so they can be very flexible. But if you're a fan of symbolic regression, you can choose to symbolically snapping them into one of the templates inside your library. Like this is like 99% likely to be a parabola, but 1% probability to be a sine. So we assign it to be a parabola. And this is more likely to be a sine, so we assign it to be a sine function. So this is and after snapping each individual function to be a symbolic function, we can assemble the whole thing according to this graph and do some further training to optimize the learning, to optimize the coefficients, the affine, some affine transformation that can still be learnable. And regarding the trade-off, it's a very nice question. It depends on whether the ground truth is indeed symbolic. If the ground truth is indeed symbolic, then after symbolification, you can get machine precision. You can get 0. You can get an exact 0, as you can imagine, right? But if the ground truth is not symbolic, then symbolification would harm the performance, which is kind of expected. So depending on if the ground truth is symbolic or not, there are two scenarios. One scenario is that there's a hard trade-off between accuracy versus symbolification if the ground truth is non-symbolic. But in the other case, after symbolification, the accuracy can even become better, as we can imagine, because the ground truth is symbolic. But there's also the question of noises, when noises come into the place. So yeah, with noises, the story is even more complicated, but that's the basic answer. Yeah. Yep.
So very interesting talk. You talked about conserved quantities whose time derivative sort of strictly vanishes, right? And I'm wondering if you could generalize this in any way. What if I have a quantity, its time derivative doesn't strictly vanish, but if I were to time average that quantity over some time scale, that time average quantity would be very well conserved, something like that. Can you generalize any of that to that?
Yeah, that's a great question. Like maybe for some systems, there are some local noises who are not very interesting, but there are some like in long horizon, there's some statistical property. Yeah. So we didn't do that, but there are some works in the literature that did that. They are not using like local objective, like trying to, enforce that the evolution and the gradient of the conservation law to be orthogonal, but they have some more global objective, like contrastive learning, things like that. I believe their methods can be somewhat integrated to ours, but we haven't explored that yet.